divided by D is equivalent to 1 by 2 of dA by A. Whereas when we are defining the Poisson's ratio, so it is defined as the ratio of lateral strain divided by the longitudinal strain. Okay, there is a transverse strain to the axial strain. Okay, so which is nothing but an minus epsilon T divided by n minus divided by epsilon A, which is nothing but an dou D divided by D divided by dou L by L. Okay, so when you are defining the volume, so V is equivalent to AL. So when you are differentiating volume with respect to L, so we'll have a dV is equivalent to, there is with respect to U into dV plus V into du. So A into dL plus L into dA. Okay. So moreover, what will be having that arena? We'll have a del V is equivalent to AL epsilon of 1 minus 2V. So AL of dL by L of 1 minus 2V, which is nothing but an ADL of 1 minus L will getting the value of an 1 minus 2V. Okay. So since del V, what we are applying that A into dl plus L into dA. So therefore, we'll get the equation ADL of 1 minus 2V, which is equivalent to ADL plus L into dA. So substitute over on it. So expand your expression. ADL minus 2V, ADL is equivalent to ADL plus LDA. So minus 2V ADL is equivalent to LDA. So dr is equivalent to A of rho dl plus L into d rho minus rho L dA divided by A squared. So as we know that we'll be substituting all this in this equation. So dr is equivalent to multiply with the value of an A rho of dl plus AL d rho plus 2V rho AL dl divided by A squared. So take the common factor 1 plus 2V. So we'll get the factor of an rho dl into 1 plus 2V divided by A plus L into d rho divided by an A. So dividing the equation, so what we'll be getting, we know that R is equivalent to rho L by A. So dr divided by R, which is equivalent to rho dl of 1 plus 2V divided by, so we know that R is equivalent to rho L by A, substitute over on it, and we'll get the expression. So resultantly, what we'll be getting, dr by R is equivalent to dl of 1 plus 2V divided by L plus d rho divided by rho. So which is equivalent to lambda is equivalent to dr by R divided by dl by L. Okay. So which is nothing but tan, which is equivalent to 1 plus 2V plus del rho divided by rho dl by L. That is the gauge factor, which is defined as the ratio of per unit change in resistance to per unit change in length. Okay. So one stands for an resistance change due to change in length, where 2V stands for an resistance change due to change in the area, where the remaining factor, which is resistance, changes due to piezo resistive effect. Okay. So what we can able to conclude that, so lambda is equivalent to 1 plus 2V. Okay. The above equation is valid only when the piezo resistive effect is almost negligible. Okay, and apart from that, the value of Poisson's ratio for all metals is between 0 to zero point 0.5. That gives a Gauge factor of value. Approximately, the value will be equivalent to 2. Okay, so this is about our strain gauge. Okay, and we'll have a two different strain gauge. So which is nothing but an unbonded strain gauge and strain gauge. So that we can see in the next class. So apart from that, when we are saying about strain gauges sensors, actually they are to be the resistive sensors, which can be deposited resistors or piezoelectric resistors. The resistive conducting path in the deposited gauge is copper or nickel particles deposited onto a flexible substrate in a serpentine form. If the substrate is bent in a concave shape along the axis perpendicular to the direction of the deposit resistor, or if the substrate is compressed the direction of resistor, then the particles themselves are forced together and the resistance decreases. If the substrate is bent in a convex shape along with the axis, or if the substrate is under tension in the direction of the resistor, then the particles tend to separate and the resistance increases. Bending along an axis parallel resistor, compressing or placing tension in a direction perpendicular to the direction of resistor does not compress or separates the particles in a strain gauge. So the resistance does not change over that. Piezoresistor differentials are often used as an strain gauge elements. Okay, so the mechanism is completely different from that of the deposited resistors. Okay, so apart from that, we'll have a two different strain gauges. There is the unbonded and bonded strain gauge that we can see in the next class. Thank you.